Everyone, good afternoon, and a warm or very cold here in Portugal afternoon. We're very glad to have you here with us for this new Europlanet webinar. We have today with us Dr. Anna Losiak. I hope I pronounced your name correctly.
Yeah, that's
so, Dr. Anna is a scientist that is, she started working with in physical geography in Poland. Anna Losiak is from Poland. Then she went to the US to study meteorites, those little rocks that all of us would like to find life in our lives. Find one, oh my God, I touched a meteorite.
Yeah.
And then she went to Vienna, did a PhD already in studying impact craters. And she made herself available to let us know a little bit more about this very interesting topic and very important topic to us here, Earthlings. So thank you very much for being here. And I will give the word to you. So if you can just say a few words about yourself before you start the webinar. We have several questions from the audience here, and which I will pose to you when you end your presentation. And if you have any question during the presentation, you have in this facility in Zoom, you have a slot that says Q&A. Please use it and put your questions here. We will then make sure that Dr. Anna will answer all the questions to you. Okay? So
I will try.
I will mute my microphone so I don't disturb you when you're talking, and the floor is all yours.
Okay. Hello, and thank you for coming to hear me talking about impact cratering, which is a topic that I really enjoy. And right now I'm studying as a Marie Curie fellow at the University of Exeter at small impact craters on Earth. So if I will have a couple of minutes left, I will be able to tell you some things, interesting things about my own research. But if I will not make it, well, you can always drop me an email and I will try to answer all the questions. I've seen some of the questions that you had posted before the webinar, and I tried to incorporate some of the answers already into the presentation, but if something is not answered fully, just let me know. I will be happy to answer it again. So the plan for today's presentation is as follows. First, I will tell you a little bit about the process of impact cratering itself, then about the effects that impact cratering and those space collisions can have on Earth and life on Earth and on ourselves, and also a couple of things that can help to save ourselves from the fate of dinosaurs. So in order to really believe and understand how important impact cratering is, it's enough to just have a look on the moon. It is a very old surface, and it's all covered with smaller and larger impact craters. You can see them with your own eyes. Those darker parts of the moon are gigantic impact basins that have been filled later on with some magma that has slightly darker color, and this is why you can really well see them. But if you have a small binoculars or a small telescopes, you can just perfectly see them for yourself. And in fact, all of the planetary bodies that we have seen so far do have more or less impact craters on their surfaces, and they are present on Mars, Venus, Mercury, and also smaller bodies like asteroids such as Gaspra. On Earth, the situation is slightly different. We do have about 190 confirmed impact craters on Earth. Confirmed meaning that scientists generally agree that this particular circular hole in the ground is not of volcanic origin or any other reason was behind forming it, but it was indeed formed by an asteroid hitting the Earth. And as you can see, it's not so fully covered with craters, impact craters, as the surface of the moon is. In fact, they are pretty rare things. If you would like to just have a look by yourself, you would have to probably travel quite a lot. As you can also see, they are not uniformly distributed within the Earth. So there is much more of them here in northern Europe. There's quite a lot of them all over United States. There's a lot of them within the Australia, and a couple of them also at the Sahara Desert in Africa. But very few have been found in Russia or in middle of the Africa or South America. Why is it? First of all, we have so small number of impact craters on Earth discovered because we have a lot of other things going on. We have a lot of geology that is very efficient in eroding the surface and removing any proofs of impact crater happening on our surface. Second of all, there is a lot of areas that are covered with water, and unless the asteroid is really, really big, it will not form a proper impact craters if it hits water. And third of all, the uneven distribution on Earth is caused by two different things. First of all, some places on Earth, on continents, are much older than other ones. So for example, the northern part of Europe is much older than the southern part of Europe. And this is why we see so many more impact craters here, because it's just had much more time to accumulate over time. While those parts here have not been kind of formed as we can see them right now for enough time to accumulate those impact craters. And second of all, well, the number of craters that we can find in a given country is very nicely correlated with the number of people that are looking for impact craters. So, for example, if we compare the distribution of impact craters within Africa, we can see quite a lot of them in those areas covered with deserts, either on the northern part or southern part of deserts, but only very small number of them in the middle part. It's very easy. It's nicely visible if you just go and use satellite images or just simple Google Earth and look through the areas in Sahara for circular features, and then check out if they are really impact craters by going there, collecting samples and testing if it's of impact origin or not. But if you need to do the same thing in those areas covered with very dense forest, with a lot of things that are really trying to eat you alive, or really hard places to travel through and see rocks because they are covered with first a lot of plants and then very thick layer of soil. It's just really not so easy. So geologists are also people, and they prefer to choose the simple way. But anyway, we did find quite a lot of impact craters on Earth, and the largest of them all is Vredefort, which is located in Republic of South Africa. It is 300 kilometers in diameter. 300 kilometers, that's a lot. Luckily for us and other potential organisms, it's very old. It's 2 billion years old. So the only organisms that were, alive at this time were very simple single cell, or maybe slightly larger, but not much, organisms. If something like that would hit us right now, we would be dead. Another very well-known impact craters is Chicxulub, which is located in Mexico. It's 170 or 80 kilometers in diameter. It was formed 65 million years ago, and it killed out dinosaurs. Unfortunately or fortunately, you cannot see it very well on the satellite images because it was covered immediately or almost immediately after it was formed with a thick layer of younger rocks. The best known and the one that is on the poster for this presentation is a Beringer crater or meteorite crater that is located in Arizona, USA. It's 1.3 or 1.2, depending on which axis do you measure, kilometers in diameter, and it was formed 50,000 years ago. And we also have two small impact craters. For example, one that is the closest to my heart, which is Morasko craters in Poland. It's actually a strong field, meaning it's a group of impact craters that were formed in the same time by an asteroid that was going through the atmosphere and kind of blow up in the atmosphere like Chelyabinsk did, but larger Chelyabinsk, and formed a group of craters about 6,000 years ago. But what defines the crater size? So why some of the craters are smaller, some of them are larger? Well, the most important thing is that it depends on the kinetic energy of the asteroid. Kinetic energy meaning the energy of the movement. When the object is moving through space, it has a certain mass and certain velocity, and then it's very abruptly stopped if it meets, for example, surface of Earth, and it cannot move anymore, but it still has all this energy that has to go somewhere, and this is why the gigantic amount of material can be moved and kind of thrown out from the point of impact. More specifically, the equation looks like that. So we can see that it much more depends on the velocity of the impactor than on its mass, because the velocity thing is well, twice as much important as the mass. The sizes of the asteroids that or planetary bodies that are hitting the Earth every day or every couple of millions of years vary between just micrometers, meaning that it's like a size of a dust, up to thousands or millions of tons. And it's also important to remember that it's important that in this equation, we have not the size of the asteroid, but rather its mass. And it may be important when you take into account that the densities of the objects that are, trying to impact us can be quite different from each other. For example, if we have an iron meteorite that you can see here that has kind of average density of 8,000 kilometers per every cubed meter, and compare it to an asteroid that is made of rocks, kind of similar to our rocks on Earth, and it can be from 1,000 to 3,000 kilometers per the same size of square cube, you can see that, they differ quite a lot. But the most important thing, as I said, is the velocity. So the objects that are impacting, cosmic objects that are impacting the Earth can have extremely high velocities. And for example, starting from about 2 kilometers per second, not per hour, per second, which is kind of the lowest limit of something that can still impact the Earth and form an impact crater, not just land in a kind of smaller pit as a meteorite, but really hit the Earth and blow up through 20 kilometers per second, which is the average velocity of an asteroid before it hits the Earth atmosphere at 20 kilometers per second, up to about 70 kilometers per second, which is expected for the objects that are of cometary origin. So just to help you imagine what does it really mean, that 20 kilometers per second, that is, well, the cosmic body is traveling. Here you can see the comparison of velocities of different objects or people. Here you have given a velocity in kilometers per hour. So I was hoping to, or I was trying to keep all the values in the same unit. And the fastest man ever measured on Earth was moving with the velocity of 40 kilometers per hour, which is extremely impressive. But if you just measure the distance that this person would cover in just single second, 1 second, is only about 11 meters. If you measure the speed of the fastest car ever produced, this is like a special racing car made for making those records that can only go straight and has some rockets on top of it, and it's really fancy. This will go only about 330 meters. So in 1 second, which is extremely, impressive, but still not enough. The plane in one, again, the fastest plane, super, supersonic, fancy plane made for making those records, will travel about only 1 kilometer during 1 second. The fastest rocket that we have ever shot down from Earth, during those shooting out from Earth, would travel much farther, and it's about 10 kilometers per second, while our very average planetary body that would impact us would travel 20 kilometers during only 1 second. So those are amazing speeds. And as a result, pretty sizable impact crater. You can see it's 1.3 kilometers in diameter. And here there is a quite sizable buildings of a really large museum here that, you almost cannot see because the crater is larger, and it is 200 meters in diameter, and it was formed by an object that was only 50 meters in diameter, and it was an iron meteorite that was traveling about 15 kilometers per second. So this is the general ratio between the object that is making the impact and the crater that results from it. It can differ slightly depending on, as I said, the velocity of the object, the material that was impacted, and also the type of the object, meaning what was its density and so on. But this is a general rule. So how it really works out. So here we have a numerical simulation of formation of crater that is about 80 kilometers in diameter, and was formed by an impactor that was about 10 kilometers in diameter, moving with about 10 kilometers per second. So pretty slow one as for the asteroid of this size. And I will show you how the rocks here will be deformed when we have this impact from the top directly to the ground. So at first, we are forming this bowl-shaped transient cavity, and this material that you can see is just thrown out from the crater and distributed around the crater. It's the thickest layer very close to the impact crater and thins out with distance. But generally, this area here is cleared out and thrown outside of the crater. You can also kind of see this very thin reddish layer. This is remains of the impactor. It's mostly vaporized, even if it's a metal. It's still, the temperatures are so amazing that it's vaporized or melted and kind of squeezed out through the entire area. So we don't have much of the impactors remaining, especially for those larger impact craters. In case of smaller impact craters, meaning less than 1 or 2 kilometers in diameter, you can sometimes still find leftover small pieces of meteorites hanging around the crater. But for those larger impact craters, it's all gone. Meaning all gone as if it was heated to so hot temperatures that it vaporized or melted and was intermixed with all the other rocks around it. And if it's a small impact crater on Earth, meaning less than couple of kilometers, we'll end up here. Well, this material will fall down here, but the crater will have this bowl shape. However, if the crater is larger, it continues to grow a little bit, and then the transient cavity becomes so deep that the rocks cannot restrain themselves from kind of blobbing up. And as a result, we don't have this, in case of very large impact craters, we don't have this bowl-shaped simple crater, but we end up with something much more complex. It is usually, it's less deep, relatively less deep. The proper depth in kilometers is much larger than in case of small craters, but it's not this very deep, simple ball. And we have a set of concentric rings. Sometimes it's just one, edge of the crater, rim of the crater, and then a central uplift in the middle. But sometimes, if the crater is really, really large, like one of the craters that you can see on the moon here, Orientalia Basin, it is 327 kilometers in diameter, and it consists of, it doesn't look like this kind of simple ball, but it consists of of a set of rings that have the same center, and well, it kind of looks like an eye. So this is true only for really large impact craters. So how worried should we be to if we are going to all die because of those impact craters? Well, we should be worried a little bit, but not too much. Happily, the rate of impact cratering is decreasing through time. On the x-axis, you can see time with the formation of our solar system 4.5 billion years ago, and the current situation being here, and the cumulative number of craters that are formed during a given amount of time. So as you can see here, in the past, there was still a lot of material, just leftovers after formation of our solar systems and larger planets. That was still hanging around in the solar system and impacting from time to time other planetary bodies. But with time, the rate of formation of impact craters was decreasing significantly. And as you can see, right now, we are in a relatively safe place. But in the very beginning of the formation of Earth and other planets, it was happening all the time that the new impact craters have been formed. Right now, this is the crater formation frequency in current times. current meaning the last, you know, billion years or something. Here on this axis, on the x-axis, you can see asteroid diameter in meters, or the energy released, assuming that they travel with about 20 kilometers per second. And on this axis, on y-axis, we can see the frequency of impact. So how often a given size of an impactor is hitting the Earth. So for example, here you can have every year, once a century, and up to every 100 millions of years. So in general, size of the asteroid and the energy released by the asteroid and the frequency or impact interval in years. So the really small impact cratering, really small bodies that are hitting the Earth are happening all the time. Like in this second, there are some pieces of dust, cosmic dust, that are falling into our atmosphere and are forming those nice shooting stars. If we wouldn't have, atmosphere that could shield us, we would be in big troubles. And this is one of the problems of you know, setting up something permanent on the moon, because the moon has no atmosphere, or nothing like the one on Earth, meaning that all the time, if you are just walking around in your space suit, you can be hit by really, really small but really, really fast piece of dust that can just punch a hole in your equipment and you know, make you in large troubles. But happily on Earth we have atmosphere that is shielding us. If the body is slightly larger, meaning 1 or 2 meters in diameter, and you can see that it also happens every year, a couple of those occurrences are happening, we can have this nice, really large bolide in the skies. Here's one that was formed, that was recorded over USA. And if everything goes well, we can end up in the very end with a meteorite, sometimes hitting the car, usually hitting the ground only. But if you have this body that is 1 meter in diameter, you can end up with a nice thing in the sky, and then sometimes also a meteorite. If we have a slightly larger asteroid, like one that happened to hit the ground in Peru, near the village of Caracas in 2007 at 11:40 local time, you can end up with this really small, only 13 meters in diameter impact crater. And this impact crater is happening, or this size of impact can happen every tens of years. In most cases, this small piece of asteroid would actually end up just like the one here, but in some cases they are especially hard and resistant to travel through the atmosphere, that they can end up forming those small impact craters and scare a cow that was just eating food and minding its own business when the meteorite hit, but no other casualties were noticed. If we have even larger impact crater, but weaker one, it can form a really, really large explosion in the sky, which happened in Chelyabinsk in 2013. There was no crater formed, but the shockwave that was going from the impact from the explosion in the sky have made a lot of shattered glass that injured about 1,500 people. This size of an impact is happening every couple of tens of years. every century, more or less, you can expect an asteroid that is about 50 meters in diameter. And this is something that formed, or most probably formed, Tunguska impactor. It's quite possible that it was especially weak and especially fast, which can suggest that it was maybe of cometary origin, but we are not sure yet. The explosion have flattened out the forest in the distance of more than 40 kilometers from the impactor site. So it was really, really large explosion. Happily, if it would go through the entire atmosphere and get to the surface, it would could have formed quite a lot of impact craters. If we have this impact crater that is 1 kilometer in diameter, this can really form quite a large problem for anyone that is nearby. Those things are happening more or less every 10,000 years, and there would be, if you would be, you know, nearby the point of impact of this asteroid, within about 10 kilometers, there would be a gigantic fireball that would be just, you know, boiling you alive. Even if you would be within the distance of about 24 kilometers from the point of impact, you could still very easily die, especially if you would be, you know, size of a human, because there would be a shockwave that could damage your lungs, or, you know, you could get hit by one of pieces of rocks that are just falling down, or being hit by whatever is drawn by the wind, and those winds would be still noticeable within the distance of 40 kilometers from the crater. But outside of the zone of about 40 kilometers, not much real damage would actually happen. But if we'll go all the way until until the asteroid that is about 9 kilometers in diameter, and if it would hit in quite specific place with specific target rocks that have a very specific type of chemical composition, you could end up killing all the dinosaurs, or most of the dinosaurs. This is what happened in Mexico. Well, today's Mexico, Yucatan, at the Yucatan. And we should expect, on average, this size of an asteroid hitting Earth every 100 million of years. The thing that the asteroid killed from 50 to 75% of all the species that lived on Earth at this point. So it was one of the large dying outs of our, you know, recorded history, biological history. What's interesting, people were trying very hard to find, you know, because to find proofs that other great dying outs were also caused by impact craters, but it doesn't seem to work. So this is the only great dying out that is really proven to be caused by the impact crater, large impact crater formation. But what really killed the dinosaurs? Because you can, you know, you can kind of imagine that if you were a dinosaur and you were just hanging around at the Yucatan area, you would, you know, be in big trouble. You would be, again, either cooked alive or just covered with a lot of material being thrown out from the crater. But, you know, there's a lot of dinosaurs that were in today's Europe or wherever else on the other side of the earth, or even just flowing in the sea. So why those dinosaurs or other organisms? Because it was not only dinosaurs that died out. What happened to them? Well, there was. It's not the actual impact that killed them. It was the long-term disturbance in the environment that was so destructive to the entire life on Earth, because they were not able to accommodate all the very quick changes and rapid changes that were happening. So if we have here the time in kind of very unspecified way, defined in unspecified way, to have a time of impact and then hours after impact, days, weeks, months, and decades, and temperature, generally higher temperature, lower temperature. So before the impact, the situation was kind of stable. The dinosaurs and other organisms known what to expect during the following months or years. But then just after the impact, the temperature rose very, very quickly, especially very close to the impact site, but also far away when the ejecta that was entering back to the, for example, on the other side of the Earth, were also very hot and traveling in very high temperature, very high velocities, and could have heated up the atmosphere in this place. And later, so first of all, the dinosaurs that were the closest to the impact point or very close to the seaside could have been just washed out or in by the gigantic tsunami wave. Other ones could have died because of gigantic forest fires. Later on, the temperature have decreased because there was a lot of material that have been, a lot of dust that have been pumped into the atmosphere that limited the amount of sun that could go through through our atmosphere, limiting very significantly the plant production that animals depend on. Also, there was a lot of acids, especially sulfuric acid, that was pumped into the atmosphere, that was later raining out as just sulfuric acid rain, very, very acid rain that could have, damaged the organism's skin and make them kind of dissolve alive. Not fully, just really terrible rash, that could lead to other terrible things to poor dinosaurs. And later on, as I said, there was a really long time before then all the dust have settled and the production of the plant material have been reestablished. So it was a lot of very, very rapid environmental changes. But what would happen? So we know what we could expect in case something like the asteroid that killed dinosaurs would hit again. But what would happen if the asteroid that was suggested in the movie Armageddon would hit us? As you remember, maybe it was about 1,000 kilometers in diameter, and it would be huge. It would be a bad idea. The crater that could have been formed would be the size of Africa. And it could have changed the day length by about 30 minutes because, it could add depending on which direction it would hit, it could either speed up or slow down the Earth rotation, changing the length of the day. So it would be really gigantic. But luckily, there isn't really any asteroids or much asteroids available for making this kind of crater in current solar system. So we shouldn't worry about that too much. But we should worry about slightly smaller pieces because as we heard before, they also can cause quite a lot of problems. So what can we do? First of all, we should be observing the sun, our solar system. So here you can see the sun and the 4 planets, Earth being here, and the asteroids that have been discovered during the given year and the total number of asteroids that have been discovered. And it was not really many of those asteroids discovered before the, as you can see, 70s, we are still 80s. But then in 94 and later, we started to really run those very intensively, those surveys of the asteroid. It was partially, well, partially it was caused by the fact that technology allowed us to do that, but it was also partially caused by the fact that Armageddon movie and the Impact movie have been filmed and shown and were very big success, because this shown politicians that it's a really good idea to give some money to scientists so that we can potentially not be all killed. So right now we know quite a lot of those asteroids. The green ones are the ones that have orbits that are not cross-cutting Earth orbit. The red ones, the red ones here are the ones that are cross-cutting Earth orbits and can potentially do some harm to us. And here is the plot that is showing similar data. So here is time from 1980s to 20th of November when I was doing the presentation, and the cumulative number of discovered asteroids divided into different sizes. So the red ones are only the ones that are larger than 1 kilometer, the orange ones are larger than 140 meters, and all the smaller ones than 140 meters are in blue. So what can we see from this plot? First of all, that we should not worry too much about the small ones, about the largest ones. All of them are right now that are there are observed, or almost all of them are observed, and we are constantly tracing them to make sure that they will not be, planning to impact us anytime soon. The ones that are larger than 140 meters, that are from 1 kilometer to 140 meters, their number is still rising quite intensively, meaning that there is still quite a lot of them that we should discover, and we should be afraid of some of the impactors that can just, arrive by from nowhere, almost nowhere, from the sky, but we were not paying attention to them and can do us harm. And those smaller ones are obviously, there's still a lot of them to be discovered. So we should not worry. In short, we should not worry about this global gigantic catastrophe that could wipe out all the humanity. This is not very probable because we know how all of the ones that are there are moving, but we can still expect some impactors that are enough to, for example, damage entire city or a region. This is a plot that is kind of showing you the same thing that I just said. We know, and it's a little bit old plot, but nicely shows what I'm trying to say. So right now the statistics are slightly better. We know almost all of the larger asteroids, but the smaller ones, this is the, well, maybe right now this would be the percentage that we know of those smaller ones, but we still have no idea about large portions of them, and we should be slightly worried about that. But if you are interested, you should check out this webpage run by NASA that is showing you what are the closest asteroids that are hanging around Earth at a given time. So for example, today is 28th of November 2017, and there will be an asteroid that is estimated to be between 11 and 24 meters, passing relatively nearby to Earth. It has a velocity of about 8 kilometers per second. But this is still, it's passing nearby Earth, but nearby Earth means 7.73 times distance from Earth to the moon. So, we are safe. But from time to time, there are even larger asteroids hanging around. For example, in 2 days, there will be one that is 83 kilometers. But again, it will be passing in the distance 6 times the distance between Earth and Moon. So we are okay for now. If you have any questions, I will be very happy to answer them right now. If not, just drop me an email. And here are a couple of really cool pages that you should visit. This one here allows you to do a very quick model of what would happen if an asteroid of a certain size hit the Earth. This is the page that I just showed you, this one here, with information about near-Earth asteroids and what can we do to really conquer the risk, except for, you know, paying attention to what is flying around us. And third link is showing you the list of all confirmed impact craters on Earth and a lot of information, nice information about impact craters. And I'm very happy to answer your questions.
Thank you very much for this very, very interesting and nicely presented presentation. I mean, I'm always delighted to see so much information that we have nowadays about the craters and so much that is to be done. And it's good to see, you know, a dialogue that doesn't frighten everyone, but provides a word of caution. So people should be aware that, you know, you can have a rock coming by and say, hello, here I am. So it's good to hear that. It's good to hear that. I don't know if you know that, but there is a program called International Astronomical Search Collaboration. It's run by Harding-Simmons University, and they have students finding asteroids. It's run by Patrick Miller, and it's a very nice program. Here in Portugal, we have over 100 asteroids found by students. And a couple of weeks ago, we had the privilege for the very first time, to have a Portuguese, a student, naming or offering a name to an asteroid. So we were all very proud for that. So we'll see if the International Astronomical Union will accept the name or not.
Yep.
But I have some questions, but I'll give the floor to the questions that we had presented to us before. We go while you can. If you feel tired, just let us know, because we really have a lot of questions here.
I'm really happy to answer them. You know, I can talk about impact craters for hours and hours, and then all my listeners are already, you know, asleep, and I'm still talking. So I'm happy to answer.
Very good, very good. Thank you for that. So, there's one question from José Rebouget from Azores in Portugal, and he's asking, do you think that God played dice? What's the probability of a cosmic event of global impact? Well, I think you already answered that.
Yes, I've seen some of the questions before, and I try to, you know, include that in my presentation. And this is the plot that is showing the approximate probability of the impact. It was this plot was prepared based on the sizes and ages of impact craters that we have found on Earth from the past. But we need to remember that it is a kind of probabilistic thing. So meaning that even though we should expect a Chicxulub every more or less 100 millions of years, it doesn't mean that it happens every 100 millions of years. It means that if we average out all the points, this is the most probable frequency. But it can happen that you know, we will have another. We will not have another Chicxulub for 200 or 300 millions of years, and then you will have two, you know, within 2 days from each other. It's possible. It's not very probable, but it's possible.
Okay, so We have another one, which is from Claudia Cocosila from Romania. She asks, is mankind ready to avoid collision of a great meteorite with the Earth? So I think this question comes very often. You kind of answered that already when you said, well, we more or less know where they are, and we know the big ones, but are we ready? So do we send Bruce Willis there, or what do we do if we know, okay, the rock is coming? What do we do?
Well, so first of all, if something like the Armageddon scenario happens, first of all, it's impossible because that 1,000-kilometer asteroid is gigantic. It's really easy to spot it. So we should not expect that. But if we know well in advance, if we have really well set it up, those systems of asteroid detection, we have a lot of time, meaning tens or hundreds of years before the possible probable impact to do something. And the easiest thing and the safest thing would be to send small spaceship that could just attach itself to an impactor and then turn on even a very small engine, and very, very slowly over those tens of or hundreds of years, just move the asteroid a little bit from the orbit that is hitting the Earth. So that's the safest one, but it usually requires quite a lot of time. In fact, even painting the asteroid in different colors, so for example, if it's a dark asteroid, painting it white, or if it's a white or whitish asteroid, painting it dark, could change the orbit in very, very in a way that we can calculate with very high probability. If there is no time, I'm not saying something like the Armageddon movie where they discovered this gigantic asteroid like 2 weeks before it hit. If we just ignore the situation and stop staring at the space and discover that something is coming to hit us within the next 2 weeks, we are doomed. There's nothing we can do. But if we still have 20 years, let's say, we can still do something. So for example, however cliche doesn't it sound, we can go there and explode an atomic bomb close to the asteroid, but not to kind of put it into pieces like the Armageddon movie suggested, but rather again to change its orbit and prevent it from hitting us.
Mm-hmm.
So there are things that we can do right now. It's just that right now that there aren't any asteroids that we know of that are going to hit us anytime soon. But even if we would find something, we currently would be able to prevent it from doing that, although it would cost a lot of money. But
well, anything will do for saving mankind, if that is the case.
Let's hope. Let's hope
that we have other more pressure reasons for us to worry about us getting out of this planet.
Yep.
Okay. So the other question is, how many craters can we find observing through the satellites?
So the quite a lot, and a lot of impact craters, especially on Sahara, as I said, or other desert-like areas, can be nicely spotted from the satellites. But in order to confirm that this is really an impact crater, not a volcanic crater, or a lot of other things that also form those kind of circular thingies on surface of Earth, we need to go to the spot, like physically go with trained geologists, collect some samples, take them to our laboratories, and distinguish if they have been subjected to gigantic pressures that cannot be formed in any other surface process on Earth. if we find those kind of proofs of this gigantic amount of pressures, or we find geochemical or isotopical traces of impactor, we can then say it's of impact origin. So the search by a satellite images, going through the satellite images is just the first step to discovering impact craters. But it's quite possible. In some cases, of course, there are some impact craters that are right now below the surface of the Earth, so you cannot see them from the satellite images, and you can only see them if by chance you have a drill core that goes through all those rocks, and then you discover some strange looking rocks and you kind of suspect it can be of impact origin, and you do those specific tests that need to be done. Yeah.
Okay. We have here also Sonia Pereira from Mozambique. He had 3 questions, but I think 2 of them, it's 2 questions, and I think one of them is already answered. So the first one is a double one. She's asking, what's the probability of Earth being hit by an asteroid? You already answered that. And the probability is diminishing over time. You also answered that. And now the question is it possible that the boundaries of tectonic plates are affected by the impact of a meteorite?
It's possible, but we don't have any proofs that this really happened. But you know, it would be very hard to actually prove because of, you know, if really an impact crater would start break in the tectonic plate, it means that most probably all the proofs of this kind of thing would be lost.
Mm-hmm.
So it's not impossible, but it's very, you know, there are other reasons for breakage of tectonic plates, and I think that if the plate was kind of already planning to get to broke down, you know, and start moving like in it's happening right now in Africa, in East Africa. And if then the impact crater would hit down there, especially like focus there, it could speed up things, but I don't think it would be the sole reason, unless it's a gigantic impact crater. But you know, it's hard to say. There are no proofs for that right now.
Okay. Let me go to the questions asked by the attendees now, and then I will go back to the list. So André Freitas is asking, is there a rule that indicates the probability that Earth will collide with an asteroid on a given mass? I think you already answered that when you presented the...
Yeah. So for every day and every larger asteroid, there is this web page, and you can check out, it's updated constantly. So there is an automatic system set it up that is first of all observing the sky for any new asteroid, and very quickly calculating automatically kind of if there is any possibility that its orbit is crossing with Earth's orbit, and or even, you know, going nearby. And then if there is any possibility, it's calculated in much more detail, and all the information are provided on this web page. So if you are interested, just, you know, about possibility of dying because of impacts on Earth, just check out this web page.
Okay. There's also a question by Paul Roach. Paul Roach, probably know him from Cardiff University.
Mm-hmm.
His team has produced also a very nice application that is the impact calculator that we use in a project called Go Lab. It's a very nice one to create lessons for the children. And he asks, there's a recent April 2017 paper by Roca, Rampino, and Presser that suggests a giant crater of the Falklands Plateau, South Atlantic, that might be the scar from an impact that caused the PT mass extinction. Do you know whether this is accepted as a realistic proposal now?
So I know the paper. As I said, in order to confirm that it, a specific randomly looking hole in the ground is really of impact origin, you need to have a very specific proof for that. And for this structure, there is no proof of this kind. So for this structure, indeed, there is some unusually looking feature in, I think, the gravity survey of this area. So it's something that should be checked, but for now, we don't have proofs that this is really impact crater.
Okay. Then let me go back here to many questions. I don't think that we will be able to answer them all, but since people presented that file in advance, let's see a couple more that you might not have touched. So there is a question here: how long the crater are still pure, hit by meteor or asteroid? As we know, on Earth we have erosion. So I think they're the question, right? I think.
Yeah, well, it depends. Highly depends on their size. I mean, the size of the crater. So the larger the crater, the more eroded it can be, and you can still detect that it was an impact crater. So, for example, the one of the craters that I've shown in the very beginning, the largest impact crater on Earth that we know of, Vredafort in South Africa. It used to be 300 kilometers in diameter. Right now, it's not the full crater that is preserved, because there was about 7 kilometers of erosion that happened. So 7 kilometers of rocks from the top was just wiped out during those 2 billion years. But because it's such a gigantic impact crater, there are still rocks that very clearly show that it was a gigantic impact crater down there. If you have one of those really small impact craters, like the one in Poland, in Morasko, or another one, small one in Estonia that I'm studying, after 10,000 years, or 10,000, 20,000, 50,000 years, they are all gone. Even though something happened there, you will not see very clear proof that it's really of impact origin. And another thing, it depends where on Earth it will be formed. Because, for example, if you would form a crater like that on somewhere, let's say in Poland, but it would happen between 2 different ice sheets traveling through this area, after the ice sheet just ripped out all the surface material, it will be all gone. So it's a very very tricky thing, but it's a very good question.
Okay, well, we still have more questions coming, and we have a long list still, but I think that you're here for 1 hour with us. I think well, you have your contact now. If you answered so many questions, you gave us so much information now to digest and research about. I'm sure that you'll be available to answer further questions to the teachers. And I don't know if you're aware, but we have several students here watching you as well. I'm sure they also have lots of questions. So
I will be very happy to answer them either right now, or if you have a question later on, just write me an email, and I will be very happy to.
That's very good. And also, you can always come to our Facebook, the Facebook the teachers. You can also put the questions there. We will make sure that Anna will receive them. And before we depart, I would like to really thank you for this amazing talk. It was really enlightening, very enlightening. We talk a lot about craters in our meetings with the schools, and it's really very nice to have so much good information. And I would like to announce the next webinar on the series of the Europlanet, which is about diamonds. Wow, next time we're talking about diamonds, precious time capsules from the deep earth with Dr. Jane Kurnev on December 13th. And you'll find this information in let me just copy this to the chat here in the Galileo Teachers page. Let me just make sure that all of you can see this. Here you have the link. So I'm sorry to all of you if you have your pressing questions here holding, but we really have to end this now. Anna, thank you so much for this brilliant talk.
Well, thank you for inviting me. It was really a pleasure.
So I hope that we will be in touch again, and that we will meet you again here, maybe in the same channel for second part of this talk. I'm sure that with there's so many questions, there is a lot more for a new session maybe on the new year. So thank you very much, and to all of you that attended this webinar, thanks for being here with us. Come back on December 13th. We have more for you, and we are also planning the webinars for 2018. So thank you all very much.
Thank you.
Anna, and goodbye.
Goodbye.